Okay, so I'm really excited and happy to welcome Rick to MSR. This is the second time he is appearing here in the last 2 years. I think in fact, I remember you came in July 21st, 2017, and you talked a little bit about how the world was going to move into the direction of edge computing as a big thing.
Well,
and so now it's kind of good to have you sort of 1 year later tell us about all the progress you've made since then. And this, as you know, we are also big believers in the intelligent cloud and edge computing. But about Rick, he graduated from UC Berkeley in 19, can I say? Should I say?
Yeah, 89.
I know, I wanted to ask you when you wanted me to say that. Anyway, so he graduated from UC Berkeley. He has a very, very interesting career. He's chief scientist now at US Ignite, and before that he co-founded a bunch of labs and things, and even in Berkeley, I think, right? And he worked in that's right. And so you also worked in HP for a while, and then he worked in SAP as well.
Yeah.
And you're also an assistant professor at
UBC.
UBC, and then you're an adjunct professor in University of Victoria. So Rick's written 2 books, has published over 125 papers, and has done and was involved with GENI when, in fact, he was one of the founders, I would say, he was right there from the very start, and has written a book on GENI as well. And also was formed the PlanetLab consortium, I think, right?
Yep.
You co-founded that. So, hey, I got it all right. So,
Got it all. Yeah.
so that's great.
Yeah.
So, really good to have you. Excited. I'm sure there are many people in the audience that are watching from their desktops. So, if you guys have any questions, please feel free to text me or somehow make it known. And with that, all yours.
And by the way, for everyone who's in the room, and for the people who are, oops, okay. Sorry. Let me check. So both for the people who are in the room, I'm gonna, we can spend an hour together or half an hour together or something, Ken? At some point this afternoon? Sure. And I really want to see Ken again, but I've booked the day to meet with people from Microsoft, and this is very much, by the way, this is a recruiting trip. I'm looking for users, I'm looking for support, I'm looking for collaborators. And, if somebody says, by the way, this is, I love the concept, boy, have you ever screwed up the execution, and I can do it so much better. Yeah, I mean, that's what I really want to hear. Come see me, because this is very much a joint effort. So, I have a bunch of friends from the subcontinent.
Now the question is, how many years, do you know?
1947. So 71.
Yeah.
I guess
That's excellent.
the arithmetic in my head. So happy Independence Day for those of you from the subcontinent.
Yeah, we wouldn't be here without that.
That's right. Midnight, August 15th. So was it midnight between August 15th and 16th, or midnight between 14th and 15th?
Oh, that I don't know. I wasn't born then. I don't know. But happy it happened.
Okay, so I said this earlier. This is a recruiting speech, and you can help build this thing. Seriously, and so the talk is on, and that really is why I'm here. So there's a lot of repeated material from the talk I gave here earlier. So for those of you who are here before, I apologize for that. So this talk breaks into 4 pieces. One is, why do you want an edge cloud anyway? Right? Well, why build this thing? Isn't Azure good enough? And the answer, by the way, the sneak peek is, I hope Dave Maltz is listening to this at his desk. Dave Maltz was the guy who told me, I'm not sure. I've got a 100 megawatt data center within 30 milliseconds of anywhere on Earth, and Azure probably has the best distribution on Earth of all the big cloud vendors. But he's not. But one of the things that I know you guys would really like to know is that good enough? And is there stuff that we can do better if we're closer to the user, and if we have better geographic presence? And so so the first part of the talk is yes, there's some examples that Victor was kind enough to give me, and motivates why you want to build this. The second is, what is it? what does an edge cloud really look like with some examples, and some lessons learned, like a bunch of them have failed and why. Then the third one is, what do we do to avoid the problems? And the fourth is, what do we do to make it useful? So here's the motivation. I mean, the overall motivation is honking big data, and we're consuming it on this, and tablets, and Chromebooks. These are thin devices, and these are thin devices which just don't have the storage or compute, and HoloLenses to do the stuff you want to do on site. So what that means is that you're doing, and that there's an awful lot of interaction with the cloud. And this is particularly true in the Internet of Things, where you're talking about sensors and gateways primarily, sitting here and talking to phones and tablets and smartphones over here, with all of this interaction being mediated by the cloud. And the problems are that the devices just don't have the horsepower to do the computations that you need to do. And I'll walk through an example of that. And so you'd say, well, okay, so let's do the computations in the cloud and use the devices either as just data collectors in the case of sensors, or as renderers in the case of smartphones, tablets, and what have you. And the answer is, well, network time is dead time. There are hard real-time constraints for a lot of the Internet of Things applications. You know, if your traffic light control comes in 10 milliseconds or 30 milliseconds, well, 10 milliseconds is probably okay, 50 milliseconds late, and you've got a bunch of bent metal in the road, right? And you have UI constraints, which are somewhat softer, but in the case of certainly a revenue application, certainly important, which has been measured at 150 milliseconds between click and answer. So that's problem number one. The second is just bandwidth problems. The data volumes get to be too large to handle over the network, particularly in the case when you think about this thing, 6 megapixels, being a multi-megabit sensor, and every one of us carries one in our pocket. It doesn't take too much to overwhelm the network with something like that. And that bandwidth problem is going to get worse over time. I've got one example here that I'll just run through very quickly. This was something we did at the Future GENI event, Matt Hemmings and me. We had pollution values over a 10-kilometer grid over every month between October of 1997 and February 2015. And the idea was that you should be able to scroll over the map and advance the month, advance the year, change the zoom and stuff like that. But we simply couldn't put the data on the device. So it was an 11 gigabyte, and we wanted to be able to render this on a Chromebook. So 11 gigabyte data set total, and that was before I got in and put in coarser data sets. Here's a screenshot of the thing. So red is high pollution, blue is low pollution. This was settable, so the color scales would change. And if you change the month or change the year, you're supposed to be able to pull down and render the data set for the entire world in 150 milliseconds, that being the real-time constraint. And by the way, 100 milliseconds of that 150 went in the browser just doing the rendering. And that was something we couldn't control. You know, you can't control. It's an inefficient client, but that's what you've got. So we spec this out as 30,000 data points for each transaction, and we could render that in about 100 milliseconds. So that gave us 50 milliseconds to pull this, which meant you've got to be within 20 milliseconds or 500 kilometers in order to do that. And that, by the way, is wildly optimistic. In Germany, this is really a sub 10 millisecond application. Demonstrated it on every continent. You can count the number of countries and time zones up at the Future Internet event. And the point was that in order to be able to do this, we needed to spread the data set to servers that were relatively close to each of the users. And the general intent is, by the way, if you were sitting here celebrating your independence, you should be able to participate in this instantly. So we didn't just need those dots on the map. If you were doing this for real, you'd need a dot on the map practically everywhere in order to do that. So that's one example of an application where in order to get the kind of response time you need a cloud server within 20 milliseconds of everywhere on Earth. And I would say actually substantially less than that. Another factor that's driving this is the cost of computation versus communication. So if you take a look at computation and communication and you put them both on a log scale, normalize it so that 1997 is 100, and run out the cost to today, you find that the price performance of computing and communication have both gone up dramatically over time. But the red curve is communication. The blue curve is computation. And you can see this is actually on a 17-month doubling curve. This is on an 11-month doubling curve. And what that means over 20-odd years is that there's been a 100x improvement in the relative cost of in the relative performance of computation over communication. And computation isn't just crunching numbers. Computation is our ability to store, process, to gather, store, and process data. And so what this means is that we're just getting much, much better at what's improving faster is our ability to grind on the spot, store on the spot, and most of all, capture on the spot than to send stuff around. And this means that the network has to change. Because the network was originally conceived as a way to ship data around, right? Basically, every network application up until about 1990 was either a small control application like Telnet, or was just some variant on FTP, right? We put different skins on it, but that's basically what it was. So fundamentally, the network was designed to send data to programs and to people. But stop and think. What a program actually does is reduce data, right? What, say, even a massive neural net AI program does is, it takes a look at this photo and it says, that thing's a cat, or that thing's Victor, right? Now, there's a lot less information, all due respect, much more important information in that thing's Victor than in the photograph, right? Like orders of magnitude less. So in general, you want to send, given that now communication is much more expensive than computation, and that gap is going to grow, you're really better off using the network to send programs to data rather than data to programs. And what that means is you need a computation point of presence near the data. So I'll give you a real world commercial example. Well, it's semi-real world. A guy wanted to scrape a bunch of accommodation websites to try and find deals and stuff like that. Put it on his, and he wound up getting snowed under by the network, just hauling all that data back rather than a small bit of information that he actually needed, right? And in fact, the sites that he was scraping would have been much better off handing him a VM and saying, here, scrape it here and send the results of the scrape back because it's slower and our bandwidth costs are going to go down. So this is something that people really should be doing much more of. And there have been a bunch of people. We're not the only ones who have recognized this. In fact, right here, the idea of cloudlets, which are small clouds that offload. And this came from I came from the distributed systems community, who was thinking about servers and stuff like that. This primarily came out of the mobile community, but these guys came to the same realization we did, which is to say the phone isn't hefty enough. We need something fairly close by to do computational backhaul for things like disaster relief, cognitive assistance, and AR for mobile users. And I think Victor has a number of strong examples in that space, and self-managing IT infrastructure for the developing world. By the way, I was talking to the CEO of Edmodo the other day. Edmodo is the world's largest educational social network, and he said, the biggest obstacle to the classroom, to putting the digital classroom in Malaysia, is poor connectivity. So one of the things that these guys really, and for various reasons, you really want thin devices in the classroom. You don't want student state. You don't want people to walk home with state. It's held to maintain. So what we'd really like is a way But we also want something that's disconnect tolerant, because because the network is flaky. I said, well, is it the local network or is it the backhaul? He said, oh, it's the backhaul, right, going through the either land or satellite. And so the obvious thing to do is to put basically a mini cloudlet, ideally something fairly hardened, because this is the world's greatest environmental condition, in the classroom with the material there to be latency tolerant. I was also talking to, I work for, as Victor mentioned, I worked for a while for HP. While I was working at HP, I did an awful lot of work for the government. One of the people I worked with there is now at whatever it is they call themselves. I forget. The name has changed a bunch of times since they were HP. But he's calling me up, and what he's looking at is something like this, and for Military Sea Lift Command. And what they want to do, because they lose connectivity on the ships, and they want to do things like, one, training for the sailors, everything from how do you get your bosun's rating to how do you work this radio, right? Which right now is going back to Norfolk over a lousy satellite connection. And he said, you spend 10 minutes waiting for the screen to repaint. So what they'd like is some localized solution that they can stick aboard the ships, where you make the interaction with the server back in the United States asynchronous with your interaction with the user. I swiped this actually from, you can see there's a little BT logo here. I swiped this graphic from a BT slide. If you guys have, I'm sure, heard about 5G, and it's going to be 1,000x better bandwidth and 100x better latency, or maybe I've got these things, whatever it is. I mean, the usual telco multiple orders of magnitude thing. And in order to understand how they're planning to do that, you have to dive into telco acronym hell. But the short version is, look, radios aren't going to get that much better. Coding isn't going to get that much better. The only thing that gets better is you move the server that serves the request right next to the user, and you put it on the base station. Of course, this being, they can't do something sensible like say a server. Instead, no, it's a DU. But yes, what they're going to do is put a cloudlet, basically right next to the base station. And that's how we're going to achieve the performance at 5G. Two other applications. This one is one of my favorites. And actually, Victor, I think you were the one who first suggested this to me in a different guise. This is your sub-millisecond use case, where you're recognizing what people are putting on a tablet. This particular suggestion, this concrete suggestion, came from a student at Berkeley, John Kubietowicz, called a guy named Tesh Moore. And Tesh said, look, neural nets, it takes a lot of horsepower to train a neural net, which is to say, you go through a lot of use cases and you derive this program, basically, that does the recognition. And that takes horsepower, and it's got to be done in the cloud. However, using the neural net to look at a bunch of photos and say, that's Victor, right? That's much more computationally tractable. And so the idea is drive the neural net in the cloud, ship it out to the edge, and then what you do is you cut out an awful lot of latency around object recognition. So that's, which can be, Victor is I'm not going to lecture on what those applications would be, because people here know them much, much better than I do. XR, right? The future of XR is untethered, right? We just are not going to sit around on our couches with goggles on, exploring the universe, as appealing as that is. So you're going to see things like cell phones, the HTC Vive, which Valve made, which is out of a design from Valve. Now that's supposed to be limited, right? You get this room that's empty, and they do the boundaries, and they can track you, and they can head track you, and so you can imagine a cable that will be long enough for that. But even so, you'd really like to make those things to be cableless on that thing, and you don't want to haul a PC around on your back. And the HoloLens, you'd really like to be untethered. In fact, the HoloLens is untethered. But so Kim Birdwell from Valve and I were talking about this, and Ken said, look, VR on cell phones is never really going to happen. because it just takes too many ergs to render a polygon. He said you can do them. Anyone can do the math. This isn't going to change, right? This isn't subject to hardware improvement. So you're just going to drain your battery. And in the case of and I know some early users of Gear VR, I think this has now been fixed, said their phones actually shut down from overheating when they were using it to render in a headset. Well, you can solve that with better ventilation and cooling. But all of these things are power intensive. Streaming video is much less power intensive, right? I mean, you can watch video on your phone for hours before the thing craps out. So the solution is to render it on a nearby cloud node and then send these things as wraparound videos. Now, you need a good radio access network for this. And I can send you scads and scads of debates about exactly how much bandwidth you need. But you also want it to be reactive. So if you change the point of view, you want to change how the video is being rendered to you. So the solution is to render in the cloud and send us videos. We're fairly sure that with 802.11n we can do it. Some people say we might need the next generation, but certainly when millimeter wave comes, we'll be able to do that. So it requires a high bandwidth and low latency connection to the device, but you simply aren't going to get that if you have to backhaul out over a 30 millisecond connection to the network. So that's the motivation, and I hope at this point nobody in the audience is everybody. Yeah. It'd be really nice to have a server near me. So that becomes an edge cloud. Well. So a cloud, I can get basically arbitrary resources, but at one of a few centralized locations, right? I mean, you guys know better than I do how many POPs Azure has around the world, and you have limited control over the location. I can tell you, put it in US West 1 or whatever, but I can't say put it in Seattle unless, of course, there happens to be a POP in Seattle and I happen to know about it. And Edge Cloud has limited scalability at a single POP, right? You're not going to put a 100 megawatt data center everywhere, but it gives me tight control over location. And that goes with the usual set of things as a mirror image. The intercomponent bandwidth in a cloud is basically unlimited, but the bandwidth out to the access is limited. The flip side is that, and very low latency inside, very high latency outside, and just flip everything for an edge cloud. Intercomponent bandwidth and intercomponent latencies are high, but bandwidth and latency, bandwidth to the edge is high and latency to the edge is low. So these things, by the way, feel complementary. I'm not wandering in here and saying throw Azure, AWS, Google Cloud, all that stuff out. No, there are absolutely things that those are good for. This is more like an extension to those things. So, but what the key idea here is that the service points of presence are first-class objects, right? The location is really, really important about where you put your service, because it's got to be there to service the user or the device. Whatever it is, the reason you're putting this thing on the edge is because it's got to talk to something outside of the cloud with high bandwidth and low latency. So where the service runs becomes the first class consideration. Well, so then this gives rise to a bunch of abstractions. The ones that came from PlanetLab as a group of related and mutually trusting services is something called a project. Right, a slice is a distributed service, which is realized as a bunch of, in the case of PlanetLab, is a bunch of containers that we're running at various sites. So essentially an overlay network of containers, and a sliver was one of those containers. So it's a point of presence of a service at a site. And as I said, we've had a bunch of these things. So wasn't one of the founders of PlanetLab. People started working on it at Mick Bowman at Intel and Larry Peterson at Princeton, David Culler at Berkeley. Started working on this in 2002. I started working with them in February of 2003, and as Victor said, put the consortium together and spent 2 years running around the world setting up nodes. So what we did, the hardware we shipped was Linux server. And this is color-coded, and the colors are meaningful, like red is bad, green is good. But we had to do our own custom control framework, right? PlanetLab Central, and we actually had to have a custom kernel and stuff like that. GENI was the generation after that. The idea was, well, build up the individual servers into racks and put a programmable network underneath it. That turned out to be a really bad idea. Once again, we had two custom control frameworks eventually, Proto-GENI and ExaGENI. SAVI was a network of OpenStack installations across Canada, 5 to 10 node rack and a configurable network. It was somewhat, this was a good thing because they didn't have to maintain it. On the other hand, they didn't have anything overlying. You had to go off and instantiate your slice at each point of presence individually. They didn't have that concept. So this came with a downside, but for reasons we'll get to earlier, this was actually a pretty good idea. Aki Nakao did a version of GENI in Japan called vNode. Paul Mueller and his colleagues did another one in Germany called GLab. It was at 17 sites in Germany. Then there are 3 more examples that are more recent. NorNet is a design for radio experimentation. As far as I know, it's still going. It's a 4-node rack that's just a board. They use the PlanetLab stack as for management. Seattle was done by my colleague Justin Kappas, who's a co-PI on EdgeNet. And this was a Python platform as a service that ran on cell phones. So the idea was that he would go to people and say, hey, please download this to help out the world networking community. It's a very restricted form of Python because we're running as a guest on people's cell phones, and you want to be very careful about the things you do, like don't drain their battery, don't get them into trouble, all that stuff. And the GENI experiment engine was something that Andy and Bavir and I did. And that is the prototype of the infrastructure that I'm going to be talking about today. And once again, all these things had custom control stacks. So those were the previous things. Here's a picture of PlanetLab in its heyday.
I know what happened in the PlanetLab case, but for all the others, how did you find these places where you were going to put these nodes?
You beg.
But it was mostly academic, or was it?
Oh, they were all universities. Well, except in the case of, so in the case of the GENI experiment engine, we ran, this was almost all sites on top of GENI. Eventually we added a few elsewhere when we prototyped the technology I'm describing here. This thing was just pure downloads, right? You know, whoever, it was like opt-in volunteer computing, kind of like Moink, right? Just download this to be nice to the world networking community. And NorNet was purchased, I mean, this was a bunch of racks that, God, what was his name? Distributed all over Norway. PlanetLab at its site, 1,353 nodes at 717 sites. We used vServers to distribute stuff, 35K kernel mod to Fedora Core 4.
It's not clear to me, pardon my aggressive question here.
No, go ahead.
PlanetLab was Edge. It wasn't, because to me PlanetLab was something quite different.
So tell me about that. No, let's please. I mean, I want to get yelled at here. That's what I came for.
Well, I mean, if you think about what Edge is doing, I mean, I think of Edge as computation offloads. So you know, you've got some devices, sensors, actuators, all that good stuff, and then you don't have the resources, so you offload that and to this device which is close to you. And PlanetLab was not that at all. PlanetLab was much more about running experimentations, and then looking at latencies to a particular cloud, or
well, so to some extent, right? But CDNs, wouldn't you consider that a form of computational offload?
No, CDN is not Edge either to me. It's not. In fact, when I give my talks, I always talk about we already have CDNs, and it's all about caching now. Because once you do computation, then you have to start thinking about multi-tenancy. You have to think about silo. You have to think about privacy, security, management. All kinds of stuff comes into play, which is not there, which is not necessarily the case for CDNs, which are much more generic and will serve 20 people.
Well, let me try this. I mean, I think of these things less as the artifacts of what people run on them. I mean, maybe this is a mistake. Okay, let's take the IDCVS example that I described earlier. Would you consider that an edge application?
I'm not very familiar with it, IDC.
Well, the idea, I mean, is look, if you're doing a GIS application, it's basically a GIS application, right? I mean, you have some geodata set and you're exploring it.
Maybe, yeah. Maybe.
But GIS right now is one of those things that hasn't moved to thin clients, right? You almost always have a fat client that you're using. And the reason you've got a fat client that you're using is because the tile set and the data set are typically too big to be sitting off in the cloud somewhere, right? So what you do is I'm trying to pull from memory the names of the various clients that do this stuff, but that's what people write. That's what's keeping ArcGIS in business, and Esri in business. So that was very much an okay. We're going to take one step back off, right? And at the same time, I consider things like the school server to be an edge offload. So you get to use Chromebooks or if you're using things like surfaces in the classroom, you're not putting any data resident on the surface. Instead, you're using the surface primarily as a terminal into an intelligent terminal into the school server. So would you consider that mobile offload?
Yeah, but right.
Or edge?
So like you talk about remote desktop in our sort of terminology. So yeah, but it's kind of like, you do something and then you lay back, look, oh, we wouldn't really act it that way. It was done for a completely different purpose and built with a different mindset and mind, and with different characteristics, different properties. But let's not belabor this here.
No. Let's push through. But I'd like to return to that because I really want to understand. Because one of the things that really frustrated me, frankly, was that Satya never used GENI. I'm sitting there thinking, it seems to me that every one of the cloudlet use cases we could have deployed and could have gotten good value out of doing it. And so obviously there's at least a miscommunication between these two communities. And I'd really like to understand that.
Another reason was that these applications that you're talking about, so I faced this too several years ago, where pretty senior people in Microsoft would say that we're going to be 30 milliseconds away, or actually now even less. What do we need it for? Like, what are the applications? So the applications didn't really exist at the time. So how could it be edge in that sense, right? There were very, very few applications. It's only now that when we look at how manufacturing is converting into need some more IT, and they need sensing has become a bigger deal, actuation has become a bigger deal, robotics, AR, VR has become mixed reality. This is when we start to see that we really need this.
Yeah, I should have put in the slide, by the way. So Kubi just got funded to do fog robotics. Kubi and Ken Goldberg got funded to do fog robotics, and the idea is that you want to have a data twin running on your This is for running on your robot, and ideally running a few milliseconds ahead, so you can send corrections to the thing. But I think the answer is, and I mean, so part of this is a leap of faith, right? I mean, the reality, and that's been the case for everything in IT from famously, right? An engineer at Intel went to Gordon Moore in the 70s and said, hey, we could build a personal computer. Who would ever want a personal computer? And, apparently he actually came up with the recipe storage idea, right? And so, all right, that's ridiculous. But the reality is, right, the applications, nobody had ever conceived of a spreadsheet until the PC existed. Nobody conceived of email until the internet existed. Nobody conceived of Yahoo and Google until the web existed.
That argument doesn't. I mean, I've heard that argument too. It doesn't. So you can go. At what point do you say was the actual invention? Do you say, well, when we created processors, microprocessors, we know how they're going to use? Oh, so that's where we really started. So you can't really do this argument that we did this and we didn't know what application would exist, but we thought they would come about Because that was not the case at the time, right? It was not. I was there too, so it wasn't the case.
Yeah. I mean, there's always, you got to. Here I am wearing a suit. Well, this is. By the way, I'm also on support. This is my begging. These are my begging clothes. So you got to go to the suits, and you got to have this credible story. You got to have like this one app that's really going to do it, right? And then but almost always that app is never the thing that makes it, right? In the case of the web, for example, the app was sharing scientific data, right? In the case of Mosaic, right, the app was the NCSA, downloading the NCSA weather satellite image, right? So, yeah, you got to have some, there's an intro app that sells the thing, but the killer app you can't imagine until you build it. So, yeah, but I agree. We're hunting for the starter app, and you're way ahead of me. Okay, so after PlanetLab, we did GENI. That was 60 racks at sites around the U.S. It was done with much more money, which is why we have this fancy map with all sorts of networks and stuff like that on it. It didn't result in nearly as many papers. Oh yeah, one thing about PlanetLab, I'm going to come back to this. That's a no-kidding research infrastructure. Anything that generates 150 top pubs at top 5 venues, and I'll grant you, Victor, this was NSDI, OSDI, SOSP. It wasn't Mobicom. I wish it had been.
Well, I'm very active in those too.
So now let's go and make it scale. And now we get to the bad news here. So what happened to all those things? PlanetLab is rotting. I mean, we still claim 717 sites. There are maybe 200 that are kind of okay, and they're all in PlanetLab Europe, or almost all are in PlanetLab Europe. Mike Wozniak is like a 20% FTE maintaining the thing. And if a disk throws Google is keeping it semi-alive as a measurement lab, but the emphasis is on semi. So it's rotting and unsupported. GENI is semi-supported. This thing is on drips of life support from Jack Brassel. Rotting, SAVI, Hadi and Al are off doing a startup. The sites are still there. You can still use them. I'm still using them. If something croaks, it croaks, right? vNode is dead. GLab is somewhere between rotting and dead. So there's a consistent theme here, namely, he's dead, Jim. There are a few bright spots. PlanetLab Europe is still alive, but they're on life support, right? I mean, it's healthy, but that's because the European Union is throwing money into it. The G has gotten kind of new life. This talk, I mean, that's me with the paddles. Clear, yeah, sort of semi-alive. Justin Kappas doesn't need a lot of money to keep Seattle going, and so he's keeping it going. And NorNet, as far as I know, is still funded and still alive. But go back to the big ones, all of which are dead, and say, what killed them? And the answer is, well, a lot of it was hardware failure. I mean, basically, so we get a grant, we buy a bunch of hardware, install it. Well, yeah, but you've got to replace it. I mean, this stuff should be replaced on a 3 or 4 year cycle. And you go to NSF and say, we need like a third of the money you gave us 4 years ago to start the refresh cycle. What? So anyhow, so for PlanetLab we needed 500. Sorry, I got those things reversed. 500, 750. No, we need $570 per year per node in hardware refresh costs alone, right? And so that works out to something like $1 million a year. That does nothing except keep the current hardware base alive. We had a problem with central support. With PlanetLab at its peak, we had 6 FTEs for 770 sites. GENI, we have 5 FTEs that did 65 sites, and these were the people who did full-time support. So that works out to on the order of between 15 and 100 people a site. These were more complex sites, and that works out to $5,000 to $15,000 a year in centralized costs, in central administration costs for each site. 2 years ago, I gave a talk at a GENI meeting saying, we ought to go big. We ought to go to a few nodes at tons of sites. And Rob Ricci, at the University of Utah came up and said, no, we ought to go exactly the reverse. We ought to go to a few bigger, beefier sites because every site is weird in its own way, and they're hell to maintain. But the bottom line is we needed $10,000 per site, to $10,000 per site per year to $50,000 per site per year, just to keep things going. And there is no way, right? Maybe for Microsoft, you could do that for thousands of sites. For academics, there's just no way. It needs to get orders of magnitude cheaper. That was the second. Then the second thing was, I can't tell you how many days I spent on the phone begging the system administrator at Moscow State to please fix the disk or to please reboot the PlanetLab node. Right? And these weren't bad guys. You know, it wasn't like I was running into hostility. It's just that, you know, geez, I got a day job, and you would not be part of my day job. You know, you seem like a nice guy, and when I get a few minutes, I'll do it for you. Berkeley, where I've been on campus one way or another for the last 40 years or 35 years, so I got lots of friends there. The GENI rack sat in the loading dock on site for a year, with me calling John Kuroda every week, saying, John, please. Yeah, I'll get to it. So the lesson is you just can't count on local sites for support. And the second big mistake we made was these infrastructure-specific software stacks, right? I mean, if you wanted to use PlanetLab, well, great, you had to learn how to use PlanetLab. You had to learn how to use that portal. You had to learn how to use that site. You had to learn a bunch of tools to distribute your stack. If you wanted to use GENI, like there were God knows how many GENI tutorials, and all of them started with the here's how you navigate the GENI portal, Omni stack, eventually GENILib, all of that stuff. And this was all done for like 1,000 users. And so there's no way that you can amortize out the cost of doing all that training, all that maintenance, all that support over that user base. Now, SAVI, and this is why I said they used OpenStack, they got to ride the wave. There's 4 big takeaways. One, that I can't do anything about. I can't go to NSF and say, you guys got to be serious about maintenance, right? I mean, I can tell them, but the record of NSF listening to me is, they could do much better at listening to me. The second thing is hardware is heinous. I mean, all of our costs, basically, and all the things that wound up breaking, all the maintenance costs with the local sites. I mean, the software was fine. It was throwing a disk. It was networks getting all this stuff, right? That was what was driving us up the wall. And eventually, PlanetLab, even with more funding, would have reached its maintenance limit. You just need to simply spend time on the sites. And the second thing is, don't write software unless you're actually adding value. And in the case of PlanetLab, there was no cloud before PlanetLab. It was the world's first cloud. So, okay, we had to write it. But Proto-GENI, really? Well, I guess even at GENI, you'd say OpenStack wasn't really mature, blah, blah, blah. Yeah, but unless you're actually adding value, don't write software. Use industry standard software, even if you have to adapt it and kludge it. Because not only do you get free maintenance, you also, and very importantly, you get free training, right? People can say, yes, it's Kubernetes. And the final thing is, look, you can't control what the sites do, but you can make it easy on them, right? You can make it the case that you never, ever, ever have to call the local admin and say, please fix things for me. And if you do that, you go from the cloud as it is. Yeah.
It seems there isn't enough incentive to do this. Like, as you said, if they're putting the rack for a year on the loading dock, it means they don't have enough incentive to actually maintain it.
Right.
And that is usually because there's a better option. So, maybe, what is that better option that instead of using PlanetLab or GENI they would use? And if that better option exists, why do you want to build this?
Okay, well, there isn't a better option, but it isn't the case that they want to do this, right? So I understand that this is, when you're talking about a research, it was what Victor and I were talking about earlier. The services don't exist that say, I really want to install this thing in order to enjoy the distributed services, right? I'm getting some real value for my side out of this. At the moment, it's just a contribution. Well, people will make contributions if the contribution is low enough. That's why people all over the world, without benefit to themselves and without a killer app, are downloading Seattle onto their phones. It's why people go off and devote their and make their screensavers run simulations to find ET, right? Or time millisecond pulsars. I mean, people have discovered millisecond pulsars at home using David Anderson software. So if you make it easy enough and cheap enough, people will download the software and will establish and will donate their resources, as long as it's essentially cost-free to them. And once those resources exist, at that point, when you have a cloud that looks like this, largely volunteer, because it's free to these people, at that point, people will start to write services that take advantage of this. Whether it's mobile offload, whether it's training, whether it's IoT sensor reduction, whether it's any of those things, people will start to write them. And they'll be experimental at first. They won't be production quality things, right? The stuff in the early web, that wasn't production quality. That didn't happen for years. But you will start to see this, and then eventually somebody's going to say, hey, wait a minute, there's this commercial service there's this commercial quality service that we can deploy on this thing. And then we'll go to the trouble of paying for it. And there's all sorts of models as how one might do that and bring it up to a 5 nines kind of thing. But it starts by saying, if you're at Moorhead State over here, all you have to do, it's 5 minutes work for you to get onto this network. And after that, it's cost-free. And if you can do that, then you'll find people will start to do this. We can give the world measles, like I did there. Yeah?
It seems like you have a bootstrapping problem, right?
Oh, yes.
So could you incent the deployment user in the following way, which is that here, we're going to give you hardware. We promise that half of the time the hardware is going to be mining Litecoin or Ethereum or Bitcoin for you. The other half of the time it's going to be running something, on the edge. And to run something on the edge, you gotta spend coin, right? And self-fund the entire network.
That's a different model than we're thinking. I'll get into the model that we're thinking of, but that's another interesting model, right? The distributed Bitcoin, will actually I've thought about mining Litecoin. Actually, I'm getting over time. Can we take this up later? That's a great idea. And there are a variety of So I still got a section to get through here, and I've been going for 54 minutes, which is why I'm cutting you off. Sorry about that. All right, so why do you want to do this? Well, latency is distance. The speed of light in fiber is 200 kilometers per millisecond. It's actually less than that because of routing bands and fiber, and you want to do a round trip time and stuff. I said fiber, but round trip time and stuff like that. But anyhow, low latency means short distance. Shorter distance to pop means more pops. There's a very simple theorem from plane geometry that says if you want to reduce latency by a factor of x, you've got to increase the number of pops by a factor of x squared. Okay, let's put a number in there. If you want to reduce latency by a factor of 10, you've just bought 100 milliseconds or 100x increase in the number of pops, which means for every pop today, you've got 100 from now on. Now that's the definition of unscalable. So let's do it. So let's think, so you talked about one way to do it differently. Let's talk about another. And actually, Randy Katz was talking about this in the early 90s. So when he was at DARPA, they were talking about digital libraries. And, it was really hot back then. Very grandiose plans. You build the data center the size of Kansas to store all of human information and so forth. Or, as it happened, this one guy in Switzerland and then another guy at Illinois built this little program that anyone could download that distributed a file. That was it. You want to solve the digital library? I don't know if approach 2 will work. I know it's a lot cheaper than approach 1. So,
I keep getting 404, so I'm not sure that.
Yeah, well, you do get. There is that. I keep getting 404s too, so people still need to maintain this. So anyhow, this is the live off the land strategy, right? And that's all of EdgeNet, right? We just use existing servers, right? Industry standard stuff, absolutely as vanilla as we can make it, and we spread by local action. You come to our site, you download a script, you run it on your server, poof, you're on the network, right? And it's been done before. The internet's spread because it used existing computers and phone lines. The web used existing internet. I mean, it was a simple overlay on FTP. In fact, the first web server was a 9-line shell script. They've gotten a little more complex since then. So that's EdgeNet. EdgeNet is to distributed systems what I'm not even going to say Mosaic. Berners-Lee original thing was to the web. Right? It's a simple little piece of software you download and attach to the network. And that's it. So no dedicated hardware. Hardware is heinous. Because frankly, clouds, clouds are not hardware dependent, right? You want to be able to run anything. And so what that means is you make them bald. And so all this hardware really was just a place where we could run VMs and containers. And what we mean is we just want downloadable images that can run everywhere. And so that makes the Edge Cloud, instead of being something that we buy and something that we spread. And by the way, Nick Teamster tried to vary into that approach. And it was very successful, he and Fabio Bustamante. So we're trying something else, but the idea is to make the Edge Cloud bottom up and downloadable. And we're not particularly targeting individuals the way David Anderson does, otherwise we'd be focusing much more on the Windows platform. Instead, it's a Linux platform, though one of the first downloads was actually to Timur Friedman's Mac, and he ran it for a while. And so it's a modern implementation of PlanetLab, right? PlanetLab was eventually LXC containers on bare metal. It started out as V servers. Now it's LXC. EdgeNet is Docker container ensembles running in VMs or container pods, which means we can run on any local cloud. And by the way, one of the goals here was that was actually an outreach thing to distributed system students at small community colleges and places like that, in particular underserved communities. Moorhead State may not be able to maintain dedicated hardware, but they sure have a cloud that they use for their own a small cloud that they use for their own local purposes. And if we make something that can run on that, they can be a point of presence here. And Ken Lutz is running it on Swarm boards at UC Berkeley. We think we can run on Paradrop nodes. Suman has talked about that, Raspberry Pis and stuff like that. So we can make any of these environments part of a multi-tenant big distributed infrastructure, which means that a node anywhere can just add itself autonomously just by local action, without even asking me, right? Just download the thing and run it. And in fact, we have an example. And I'm going to do something very risky, which is I don't do live. So first of all, note the date up here. It was 2135. And so he's just running the setup node script. I've cut out a little bit of this so that you don't have to sit through a minute worth of video, mostly just downloading packages. This is all running at the Cornell site. Eventually, sometime soon, he's going to type in the site name. Hi there, I'm Cornell. And it's going to check and say, well, is Cornell taken? If Cornell is not taken, guess what? You can go be Cornell. And now it's finished at 21:36:36. So a minute later, that node has been added. And in fact, we go to the EdgeNet portal, and there's Cornell there. So a node can add itself in under a minute. And that's just your basic Ubuntu 14.04 VM. Eventually, we're going to make it easier than that. Just have an image that on boot prompts and says, what's my name? But, and in fact, we might even assign it the name before download. But right now, there are too many VM images for us to do that. Okay, making it a platform. I'm already at the hour, so I'll go fast through this. So the key foundational layer is distributed services deployment, right? Just you want to be able to deploy across this thing using standard technology without learning any new tools. I mean, it's not without learning any tools. Obviously there has to be some way to do this, but using industry standard technologies, the way that SAVI was based on OpenStack. And one other improvement we wanted to make on PlanetLab was PlanetLab had a single container as your point of presence, and which has a variety of problems actually. Like the container has to support SSH, which means we need curated images, stuff like that, because because you have to be able to control things. You want something that supports ensembles of microservices because that's the modern way to deploy, and it's much less problematic. And we want it to be an industry standard. So the other point is right now, raw Docker is designed so that the ensembles of containers are contained within a VM, and the control is from the VM. And we wanted to get rid of the VM per user entirely, and just go to, which meant that it had to have an infrastructure that permitted ensembles of containers to be controlled from outside the container without shell access to the underlying VM or machine. And fortunately, and so that was one of the design constraints. We also need to be able to share popular ports. We haven't done that yet, but we have a plan for doing it. And we need to use standard tools for deployment and orchestration and for control. What gives us all of those things, except for the port sharing, which we know how to layer on top of, is Kubernetes, which you guys are familiar with. So in fact, Eric Brewer, who is now the VP of Cloud something or other at Google, says VMs are a transitional step in cloud technology. It's what you really want is just to manage container ensembles directly, and they've developed the tools to do it. 12 years development of Google adds Borg, so it's now mature and well tested, and God knows it's well documented, and there's lots of training. So we decided to pick that. EdgeNet is, so now that's EdgeNet, right? It's Kubernetes across the wide area. There you go, with nodes joining in a minute. Now you know everything there is to know about it. It's up and running at 34 sites, more or less. I mean, sites add all the time. Sites drop, what with one thing and another, but at least VMs. You know, if a VM craps out of the site, that happens all the time. And there's recovery mechanisms, many automated, that are there. It's not like a hard drive throwing a disk. So this is a joint project between the US, EU, Japan, Brazil, and Canada. One of the reasons this is going to grow is because the PlanetLab Europe sites have been screaming for something like this for ages. And Tamir Friedman said this is the answer to our prayers. So we're going to, I hope, deploy most of PlanetLab Europe will, I hope, become EdgeNet within the year. So you can map, this slide is nothing, it's just mapping the classic distributed systems concepts that we know about to the way Kubernetes talks about the world, which matters for the architecture, because what you want to do is use these you want to map these native concepts as closely as possible one-to-one to the distributed systems concept so that it feels natural to the user and so it's natural to implement. So the user experience, there's going to be one more video, is you log into the EdgeNet portal, which I won't show, using actually your Google ID. I've got to fix that and make it more. I've got to implement. Never mind. It's on the punch list to make that better. Agree to the accessible use policy. You get approved by hand. You know, I get an email and I say, and I approve you. And then about 10 minutes later, you get your own personal namespace and a config file that the next time you log into the portal, you can download it. After that, by the way, you never need to log into the portal again. Because the only thing this is actually managing for you is the configuration, is your namespace and configuration file. You've got both of those, and then you can use kube control on your local box if you want to. We also provide a dashboard, which I'll show you in a second, as a convenience, which you can use to manage your slices. So let's show our hello world going around the world in 5 minutes. By the way, I have a 5-minute rule on infrastructures, which is that if your infrastructure takes more than 5 minutes to run hello world, it sucks and I will never use it again. So this has 2 files. This is the Docker file to build the container that I'm going to deploy around the world, and all it does is just downloads an image and then runs, and then does a curl to a server where I've got, which is going to show a map that you'll see in a bit. That was the deploy.yaml file, so it was about 8 lines of code, and it says, here's how you deploy the container. Now I'm logging into the dashboard that we provide as a convenience, going to my namespace. and I've already logged in. Ordinarily, it would prompt me for that. So, or no, and I say I want to create a daemon set, upload a file from my computer. If I were quicker about this, we would create from file. I upload the deploy.yaml file that I showed you earlier. Say upload. This would go faster if I were faster at the keyboard. And now I'm going to the site, and you can already see we've got a half dozen. It's already deployed out to 6 sites. As it deploys out to each new site, another dot will appear on the map. Because when the server gets curled, it deploys the site, and eventually, within about a minute, the 25 sites we have at the time all said hello. Yeah.
So when you deploy that Kubernetes configuration, it's deploying that container at all sites?
Yeah, that's because, sorry, I should have expressed that. Actually, this is a deeper discussion, but the quick version is that there are two kinds of, that you can either deploy services, or replica sets or daemon sets. If you deploy a daemon set, that means I want a copy on every node in the infrastructure, and that's what I selected. If you do a replica set, which is I think most of the way people are going to do things, you're going to say I want X many copies, and I want them on nodes with these labels.
Okay, so it's label
And
based.
yeah, and so we use labels to distinguish that.
Okay, that was going to be my next question.
Yeah,
Can you use labels to control placement?
Yeah, we use labels to control it, and it's up to you to do the labeling.
Okay.
Though what we're going to do, because labels are namespace specific.
Yeah. I
But,
use labels in mind to control
one of the
placements.
zillion things that's on my to-do list. And oh, by the way, anybody who wants something that's on my to-do list who thinks they can do it better, and if you know Kubernetes well, you could probably do it better, is to write a labeling service, which would just drop you a YAML file with your which would pre-fill a YAML file for you that you could then download and tweak and then upload again or use kube control with, right? So the idea is just to be a labor-saving device for you.
Yeah, okay, yeah.
Yeah.
So, yeah, I do a lot of labeling now because when I do experiments, so one of the problems that I have is the randomized scheduling of Kubernetes. It will just try to figure out how to place the things so that it fits within the constraints. And so that's really bad for experiments because you can end up with like a bunch of things collocated together that shouldn't be. And so, yeah, the labeling is super important.
Yeah, the labeling is important. And I don't think we've got, by the way, the right mapping yet. Because one of the abuses that we're doing here is we're taking, right, because the Kubernetes' big idea is that all of the nodes are homogeneous, right?
Yeah, that's the problem. Yeah, exactly.
And for us, the nodes are all heterogeneous.
Right.
And so what we've got to do is, and so we're grossly abusing the system to do this mapping. And our horseback idea of how to do this is to give each node a label, to say, to make the number a different label, to make the number of replicas exactly equal to the number of labels that you want, right? And then say only put it on nodes with these labels, and I want one on each node with each label. In other words, force a mapping onto individual nodes just by constraining the scheduler very tightly. But I'm not sure that that's the right thing to do. And in fact, how exactly do you do that? Now, mind you, that's really an engineering question, because it's a question of how do you abuse Kubernetes to do the thing that you really want it to do. And we want to do a big thing, and Kubi is, as you can imagine, is all over. How do I, what do I do about somebody who joins the system and then does a memory dump of my secure stuff? Because Kubi is a fanatic about security. So can we label nodes so that we say, yeah, this thing is trusted. Either we know the guy who downloaded it, or we know that it has hardware features that makes it trustworthy, even if the operator is untrustworthy. We want to deal with the CAP theorem with latencies greater than 50 milliseconds. By the way, India is doing some of the world's leading work on that. Okay, I'm 10 minutes over, so. And this is just the base layer. We need much more on top of this. We need composable services. We need persistent slices that have services running in them that people can just use. We need persistent deployment files that you could just bolt into whatever it is you want to do, which is the equivalent of a library. I'll skip the layered architecture slide. Everything is left to build, and here's the big incentive to help us with this. 150 papers on PlanetLab in 5 years. And I'm not talking, the FUBAR conference, NSDI, OSDI, SOSP, Infocom, Sigmetrics, right? SIGCOM, right? Conferences at that level. And if you go back and you read the papers, they were all about building infrastructure in PlanetLab. This thing needs infrastructure as badly as PlanetLab did, which means that if you're sitting here telling me, I've got a better idea about how to build that, there are no guarantees. But the history is that there's a ticket to a top-tier venue for you to publish that. All right, so tons of things to do. I can't do them all. You guys can do most of them better. I have tons of collaborators, including one from Microsoft, of which I'm very proud, and I thank them all. And with that, that is the end of the talk. And I'm sorry I ran over.
It's great. So yeah, got a few questions if anybody wants to ask some more.
Go ahead, Shadi.
You mentioned like one of the big issues you had was the maintenance of it, like with hiring all of those FTEs.
Well, that was my big issue with PlanetLab. Yeah.
Yes. Isn't this just going to get worse than that?
What? Tell me why.
Because there are many, many more nodes, and your idea is like anyone can plug in something, and who's going to monitor it? What if something fails?
But the point is, if it craps out.
I don't see how that issue got solved, and I just feel it's a bigger problem here than what it was before. Because it's even more heterogeneous. Anyone can plug in any device, just run a VM on it. And
as long as it runs your software, do you care?
I want my software to be running reliably, so I want to make sure it's running. And what if
Oh, but this is absolutely the case in every district. In fact, if you go to one of your data centers, I'm willing to bet that at any moment, 10 to 15% of the nodes in that data center are crapped out.
Yes, but the data center has some dedicated people that make sure that if it's down, they'll do something about it. They're just pouring money to fix the issue.
Yeah, but what they'll do is they'll migrate. But in the meantime, your stuff migrates seamlessly over to something that is still up and running. Right. I mean, I know less about the Azure data centers. I know that in the Google data centers, the G boxes are jokes, right? I mean, they're open. The hard disks are Velcroed on, right? Because the general idea is, well, they're designed so that if something craps out, well, you just pull the disk off, slap on a new one, and bring that sucker up. So this is actually one of the challenges to say, okay, every node can be insecure. Every node can be unreliable, right? But stochastically, if I have enough of them, something's going to be running. And then I've got a problem. One of the big problems that you obviously then have is to have a service that migrates service points of presence seamlessly from a failed to a working node.
And PlanetLab didn't have this feature?
Oh, PlanetLab had nothing.
Okay.
PlanetLab eventually it did, right? But no, I mean, the PlanetLab guys did the same thing we're doing, which is they provided this bare service, and then they said to the community, go off and, if you want that, and that's a good idea, go off and build it. And a lot of people did, right? Stork, Codons, CoDNS, CoDeploy, right? All of these, dozens more. The DHTs were designed for that failover, right? So so there's been lots of people who have looked at building stuff like that. But so issue one is the service has to be reliable even if some of the nodes go away, right? That's the system problem. Issue number two, and this is the maintenance problem. The PlanetLab have, Moscow State goes down, I got to go out and fix it. Or I got to arrange for somebody to go and fix it. And if what you've got is a box sitting in the corner, right, that's throwing a disk, that means shipping a new disk, it means somebody plugging the new disk in, all that stuff. If it's VM, boot the VM on another server in your, boot that VM on another server. You do that all the time. So it's the second issue that this solves. First one is still out there.
Essentially, Kubernetes decouples the hardware failures from software reliability.
And that's the other point. Kubernetes takes care of a lot of that.
Is it respawn stuff?
Yeah, it responds.
But still, somebody has to fix the hardware issues as well. You can't just throw away machines the moment they fail. Like, who's
But I
going
think
to...
that's the thing.
No,
I don't have machines. I
don't
think
have
that's
any
the difference
servers.
here. Like in PlanetLab, there was hardware. Here, you're just saying run this software on your hardware
So you're
that
in
you're
charge
already
of
maintaining.
maintaining that
Yeah, because it's
hardware.
your machine that you're running this
That you're doing other stuff
Let
on.
me ask you a slightly different question. So I don't know if you know about Azure IoT Edge. So the concept there is the same.
Yeah.
Essentially, there's a binary you download, SDK, light up a container on Linux box, it fires up, you got ESA services, you write Azure functions, Lambda functions, and you have an edge which is connected to the cloud.
Yeah, that and Amazon Green Glass.
Yeah. So now, but there's sort of if you think about, so PlanetLab I get, the EdgeNet I'm not sure, because the idea is, to me, the edge idea is you're offloading and you're building and you're basically doing computation on this device, right? So inherently, you're not actually saying that I want to do computation on a device that is sitting in India or China or something else. You're doing it on premise on this device. And you got the cloud to back it up. So I think the business model is very intertwined with the use of it. Like in terms of academia, you sort of said the one goal would be get 150 papers. Well, I could do that today. I could get, for example, Azure IoT. It's free. You download it. You put it on a PC. You do your offloading, and then you do it. So I don't know what is EdgeNet buying me. Like what am I getting that I don't already get with
From Azure, I mean that's so. We started off on this project before Azure IoT Edge, and so it may be that we've been overtaken by events, in which case I will be very sad.
No, I'm actually trying to work with you. I'm trying to figure out that there's got to be there has to be some value that this one provides that is not provided by AWS or Greengrass.
Yeah, I mean the idea behind the use case that I've seen for Azure IoT Edge and for Greengrass. Greengrass or green.
Greengrass.
I mean, when it gets stuck in your head the wrong way, you just can't get rid of it. But the idea is that the use case for that is that that I'm running. I'm actually doing stuff on Azure IoT. Yeah, it's because I'm running a factory, right? And I'm doing most of my stuff out on the Azure cloud. But what I really want is a local point of presence here that hooks up seamlessly to the Azure cloud, and that's what Azure IoT Edge gets me, right? And that, by the way, is a great use case. This is designed for someone who may not exist. EdgeNet is designed, and the person who it's designed for is somebody who wants to deploy a global service that's accessible anywhere, right? So yes, so one way to think about it is yes, you could do this.
But Edge is not a global service. See,
but well.
And even if it is, you cannot then rely on users managing their machines.
But
You can't say
fundamentally
somebody
it's
else
not
is
a
going
global
to.
service.
Yep, I agree, but even if you think of an application that is, then you cannot put that burden on the person that's bringing in the machine. So if I'm using somebody else's machine, I can't say, okay, they're hopefully going to maintain it and take care of it. Then you actually have to provide the
No, but the point is that I can rely on. Well, you're right. I can't rely on any one individual. But look, 20 years ago, David Anderson built the world's greatest supercomputer entirely on volunteer downloads, right? And by the way, it's still going, right? There have been millisecond pulsars which have been discovered by Einstein at home. So Stardust at Home project. Now these were people who were doing citizen science. Found cometary dust in the Stardust spacecraft. So people do volunteer things, right? Institutions volunteer things, particularly if you say, and where I'm really pointing this, is frankly at the science DMZs. More than anything else. So if I had to pick an early set of application users, it would be the science DMZs. And I'll give you a good example. The nanograph project it is looking at the series I know a lot about millisecond pulsars, is looking for gravitational waves by looking at variations in pulsar timing. Now the database is huge, because you've got all of the millisecond pulsars. But the basic work is to do timing analysis on a single pulsar, and the data set for that is much, much smaller. So what you have is a large data set that currently sits in a couple of repos. One is in Cornell and one is at West Virginia, and it's being looked at by a worldwide community of scientists. But each scientist will only look at a small chunk of it at once. So this sets up very nicely for a distributed computation network, where what happens is you have a network of Jupyter hub servers that talk to each other, and that have a single global file system, which with the repo sitting back at Cornell and West Virginia, but with all the local accesses being in a cache local to the system that's sitting off the Jupyter hub. So on the one hand, for the universities that are maintaining the science DMZs, they're getting much less bandwidth use, and their services are getting hit much less hard. And by the way, the people who really wanted to use this distributed stuff were the people at Cornell and West Virginia, because they were saying, we're going to get killed when we find a gravitational wave, and we will. We're going to get killed by everybody around the world coming in to hit on our servers, just because everybody's going to want to check that data. So we desperately need a data distribution and computation distribution solution, which is why they want to use it. So that, I think, is the use case which will at least appeal to the universities, right? Which is distribution and computation on distributed scientific data. On scientific data.
Similar to what Grid was trying to achieve in the smart grid.
Yeah, well, why does that computation have to be done at the edge, right? Why can't that be distributed into the cloud? Like, is there a strong latency need to the end user?
Yeah, there is actually. Well, there's certainly, if you're working, the answer is part of it is just a bandwidth issue, right? Which is that I don't want to distribute the entire data set. I don't want to distribute the entire data set out to the edge. I just want to distribute the chunk that you're working on. And yeah, I don't want to. And yeah, there's a latency issue, because you do a little computation, you do a plot, then you do a little bit more, you do a plot, stuff like that. You really don't want. It's not as stringent as the latency issue going back to on the visualizer that I showed, but there is one.
The one use case that I can sort of see this is, I can think of this as but actually I don't know how to address Shadi's point there, but I can, you think of this as a public infrastructure available, and you opportunistically use it. You certainly can't, I mean, she's totally right, you certainly can't build things that you are going to depend on a system that when it go away is not managed or monitored by somebody, or it doesn't get replaced if something happens. So you can't build anything like that. So what you can do is opportunistically use it. You look around and see you've got some compute nodes available to you, and it exposes itself as that, and then you offload something on that, and it does it for you, and then you walk away.
Yeah, I think that's right. But I also think there are people who are going to want to. Well, first of all, I think that's one use case. I think another use case is that frankly it makes a lot more sense for a university or an enterprise administrator to join this thing, right, and slice off some hunk of these things and offer computational services to customers, other users, other users, stuff like that, rather than having them pull down data and compute at their own site. Right. So my general sense is that the reliability is going to come, Shadi, to your point, from people who consider it in their own interest to maintain an EdgeNet node, and thus will devote the effort to making sure they do it. But you're perfectly right. If this is just downloaded by people sitting at home, and it's going to flake out any old time, well, you know, I mean, it works for Seattle, right? Stochastically, you've got a good chance of getting a Seattle node wherever you want it. Is it going to be reliable for this use case? That's a good question.
Okay, I've had people that I need to, I guess, go. But thank you so much.
Well, thanks for having me. And by the way, I'm on camera.